Let's take a look at number 7 from the first midterm. So number 7 was the most difficult problem on the midterm exam. What have we been asked to do? It says provide a synthetic pathway for the molecule below, A. I apologize, I forgot to put A there. Starting from 2-hydroxymethyl-cyclohexone. So here's the here's the hydroxymethyl group and the cyclohexanone. So this is our starting material. Also, we have to recall that this big wide arrow, that's not a reaction arrow, that's the arrow we use when we talk about a retrosynthetic analysis. So I want to make this molecule. This is one of our starting materials, and we have to figure out how to make this starting from this material. It then tells us that you may use any other reagents you deem necessary so long as they have fewer than 3 carbon atoms. That means it can have 1 or 2 carbon atoms in any of the other reagents we deem necessary. It says please include conditions, and then a final question, would you have any major side product after the final step? If yes, what might it be? So how do we do this? We can see this thing here, which is an enamine, and we know that we can make that enamine from dimethylamine plus the ketone. We also have to attach 2 methyl groups to this carbon, and from here, what reactions do we know where we can make carbon-carbon bonds? We've only done a couple in the course so far, and we know that we can't just add methyl groups to this alcohol functionality. What's the reaction that we know we can use to make carbon-carbon bonds? Well, we know that if we have a carbonyl group and a Grignard reaction, we can make carbon-carbon bonds. So what are we going to use to make these carbon-carbon bonds? Well, let's think about it for a second. Can we convert this to a carbonyl group? There's different ways we can make that a carbonyl group, yes. And then we can go ahead and attach our methyl groups by converting this into a carbonyl group. So somehow we need okay, and I don't know what that's going to be, but here I'm going to add methyl magnesium bromides. But I want to get, what I want to be able to get to is this somehow. Okay, so somehow I want to get to this. How am I going to do that? Well, I need to think about this some more. There's a couple things I can do. One, I could react this with PCC. And that gives me the aldehyde. I could react that with methyl magnesium bromide. And that will give me what I want, but there's a problem. We have to work this reaction up and everything. What's our problem? Well, what keeps methyl magnesium bromine from reacting with this carbonyl? Although this is a much more reactive carbonyl compound, methyl magnesium bromide would also react with this carbonyl compound. Can we protect one of these over the other? Might be difficult to do. In fact, if we tried to protect, this is the more electrophilic carbon. This is the carbon that is more, the carbonyl group that is more likely to be protected if we tried doing it with one equivalent of some protecting group. So this is not really a viable reaction. We could protect this first and then oxidize our alcohol to the aldehyde, but that oxidation reaction is done under acidic conditions as well, so we're likely to deprotect it. So this is, although a promising, it's not a very good pathway. So let's think about that a little more. What else can we do? Well, what if we react this with Jones reagent or some other strong oxidant? And we get the carboxylic acid. We can now react that carboxylic acid with something like ethanol and make the ester. That's nice because now we have a carbonyl group and we have an ester. We know that esters react with Grignard reagents, so do ketones, so what are we going to do? Now we very nicely have quite a reactive carbonyl compound, and over here this one is less reactive. We can actually protect this by doing this reaction with a little bit of acid catalyst around, and we have to make sure that it's dry. Why do we have to make sure it's dry? Well, if there's any water around, we're going to remove this ester group. We can actually protect this under certain conditions where there's no water about, but we have a small amount of acid and our diol, which forms this ketal group and protects this. Now we can react this with two equivalents of methyl magnesium bromide or iodide, in fact, and we did that in question number 6. So we initially make the ketone product, which then reacts with another equivalent. We actually need 2 equivalents of methyl magnesium bromide, and we end up with this final compound, which we can work up under acidic conditions and water, and that does 2 things. It protonates this oxygen and then actually removes our protecting group, so we end up with this compound. And that we can react with dimethylamine under acidic conditions to get our final product. Okay, so this reaction is going to work. Had you tried making the aldehyde, you could end up getting small amounts of product, but it would be very difficult because you can't protect selectively that carbonyl group versus the aldehydic carbonyl group. Now let's think about this for a second. This final step where we're reacting our secondary amine with a ketone to form the enamine. And let's think a little bit about the final question that we asked. What would the side product be? Well, when we go ahead and make this enamine, there's actually no reason that we couldn't remove the other and this would be our major side product.